All right, so if you have a periodic table labeled in this way, now that doesn't mean that these elements are S sublevel region elements, but their location represents filling of that sublevel and will help you write the orbital notation properly. Okay? So that's why we did this, so you know where those are. You need to memorize this periodic table. If you did it at home and you labeled it, you should be halfway there memorizing it, maybe all the way there in memorizing it. Okay, sounded like somebody has it memorized because they could tell me right away what level that was. Okay, and that's a good thing. We've been working with it when we write orbital notation, so the more you work with it, the better you're going to get at it. But if you don't do the homework and then use the homework for the orbital notation work we do, you're not going to have it memorized. So you're getting the opportunity to memorize it without really any extra work. So unless you do your part, you won't be able to get there. Okay, you'll have to do extra work if you intend to pass tests. Okay, so we use that then to figure out the areas or the orbital notation. So we have to know that. We have to know the layout of the periodic table. So we know that these first two columns with helium moved over here is our S sublevel region. These last 6 columns is P, and this is D. We will not be writing any orbital notations in this class that include F sublevels. Okay, we're going to stop with the D sublevel regions. Okay, all right. So then, what we learned to write, if we use copper as the last one we did, we have to start with the very beginning. So you're in the first energy level. That corresponds to, it's not the same thing as, but it helps you to figure out how to write them when you know that you're in the first primary energy level. Helium moved over here, and hydrogen, that makes up the first primary level. That's the first row on the periodic table. So we start with row 1, and both hydrogen and helium here are in the S sublevel region, so the electrons there are in the S sublevel. And we're going to start out by putting, when we get done, we're going to have 27 electrons, 29 electrons for copper. Okay? We're going to start out with the first 2. There's the electron that corresponds to hydrogen. And then we're going to put the electron that corresponds to helium. Okay? And then we're going to go to the second primary energy level. Okay? And so this is where we are, second row. That's the second primary, or corresponds to the second primary level. And this is the S sublevel region. We always get to S first. So second row, second primary energy level, S sublevel, because it corresponds to the S sublevel region I showed you on the periodic table. And we're going to put our second 2 electrons in here, corresponding to the location of lithium and beryllium. One up and one down. Once we finish beryllium here, then we're ready to go over here to where boron is, still in the second row, but now we're in the P sublevel region. So these are 2 P electrons. 1, 2, 3, 4, 5, 6 elements here in this row, corresponding to 6 electrons we're adding, and you can only put 2 electrons in an orbital, so we need 3 boxes to represent our 3 orbitals. 1, 2, 3. And boron, carbon, and nitrogen all are going to correspond to up arrows representing electrons with a positive spin or an up spin. And then oxygen, fluorine, and neon represent electrons with a down spin or negative spin. Okay? The reason we call them spins is because that's how we explain how you can put 2 electrons with the same charge in the same region. Things with the same charge, if you remember from physical science, tend to fly apart. Did y'all do the pith ball demonstration? No? I see somebody going, what? Okay. Yeah, well, what you did, if you use the pith ball demonstration, you have these little tiny balls on a string. You get one of them charged positive, or 2 of them charged positive or negative, and they want to fly apart. So you hang them together and they'll fly apart. Then you get a pith ball and something else you charge into positive, and they want to stick together. Okay, showing you that positive things fly apart from each other, negative things fly apart from each other, but positive and negatives tend to stick. So the way we get electrons together is we have to cancel that repulsion. Okay, the opposite spins is the way that we describe canceling electromagnetic repulsion. Okay, now that's something you need to know. The reason they have to have opposite spins is because we have to cancel the electromagnetic repulsion to get them in the same orbital. Okay? Electromagnetic things with the same charge have electromagnetic repulsion. So to get the electrons in the same orbital, we have to cancel the electromagnetic repulsion, and that's what those opposite spins are about. Yes? All right, so that's the whole second row now we've gotten done. We're ready to go to the third row. That begins with sodium over here. Okay? So that's the third primary level. And we're always beginning in the S sublevel because those are our first two columns. So we're going to start with 3s, only one orbital in an S sublevel. So we've got 2 electrons there, and we filled up the orbital notation through magnesium here. And now we're going to go to aluminum. Well, that's in the P sublevel region. So we're still in the third row, representing the third primary energy level for a ground state electron or ground state atom. 3p. P sublevels are always going to have 3 orbitals. And we've got to fill up that whole row there, so we're going to put 1, 2, 3 electrons for aluminum, silicon, and phosphorus. And then put the second electron with a downspin, sulfur, chlorine, and argon. And we fill them up in that order because if you don't have to put 2 electrons in an orbital, they won't go there. So you're going to put 1 in each box, and we call that the school bus rule. Okay, we used a little story of you guys going to school on the very first day and you don't know anybody and so forth. Alright, so now we're getting into the row that involves copper. So here we are at 4th row, S sublevel region over here. 4s. And there's the electron for potassium, and there's the one for calcium. Potassium and calcium. But here we're entering the D sublevel region. The D sublevel region is not in the 4th primary energy level. It actually is in the 3rd. So we're going to write 3D. Okay? In the first energy level, you've got 1 sublevel. In the second energy level, you have 2 sublevels. In the third energy level, we're going to end up with 1, 2, 3 sublevels. Every time you go up 1 primary energy level, you can have that same number of sublevels, although we don't necessarily fill them up immediately. In this case, we had to put 2 electrons in the 4th level before we could fill up the third sublevel of primary level 3. So there are 10 atoms across this section here, representing 10 electrons. And to get 10 electrons in that sublevel, I need 5 orbitals. So I have to draw 5 orbitals. Even if I don't have even if some of them are empty, you still have 5 orbitals. 4, 5. Okay? All right, copper has 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons. 1, 2, 3, 4, 5. And go back and pair it up. 6, 7, 8, 9 electrons. Okay?
Take 1 from 4s.
Right. It's better if you take 1 from 4s. Okay? If you wrote it like that, I'm probably not going to count it wrong, but it's better that you know that when you get an almost full, half full or almost completely full sublevel, D sublevel, only what happens in D. Doesn't happen in S, P, or F, only in D. Then really what we want to do is take an electron out of 4s and drop it down here to fill it up. That's because the electron cloud is far more stable when you do that. And the universe likes stability. Okay? So that's where we are on orbital notation. Now, how does that tie into the balloon models? Yes?
Do you only do that when the 5th sublevel isn't complete, or do you do it when the 4th one?
Yeah, it's when you're missing, either you've got 1 electron in 4 of these, you put a 5th one here,
Right.
or you've got 9 electrons, you'll put a 10th one here.
Okay.
And that only happens in that D sublevel.
Okay.
3D, 4D. There is an exception in 5D, but we won't even get to that because we're not going to be filling up F sublevels. Okay? So don't worry about it. All right. So it is better if we take that out and put it down there. Now, how does that relate to orbitals? S orbitals are spherical. And we said that if we were drawing only S orbitals, here's the nucleus. And the first primary energy level, say, as long as the electrons are in their ground state, has this, takes up this amount of space, it's spherical. Well, the S sublevel the outer regions of the S sublevel are the same as the outer regions of the whole primary energy level. Okay? So the shape of the S sublevel is the same as the shape of that primary energy level. Okay? So S only has one orbital. That's all we're going to have there. Okay? One sublevel. All right? Then when we get to the second primary energy level, we still have this S sublevel. That's the first one we put electrons in. So it's a sphere. I'm just sort of drawing some shading here to help you visualize that that's a sphere. So this sphere representing the first primary energy level is inside this sphere, which represents the second primary energy level. This sphere also represents the range of the S sublevel in the second level. And the P sublevels will be inside here, those double balloon shapes we talked about. Okay? So it starts to get kind of complex if we try to draw all of it together. So we kind of separate them out, but mentally you need to be able to think of S sublevels being here and the P sort of tucked inside there. Okay? And then if I were to go to the third primary energy level, I'd have another S sublevel corresponding to the same range and region as the primary energy level 3 itself. Okay, so we shade that out, and there's your third primary energy level. It's also the same shape as that S sublevel, and P is stuck inside there. Okay? All right. So if we were to look at that third energy level as a separate thing, so here's the nucleus down here, and here's the third primary energy level. Okay? P orbitals are going to be double balloon shapes inside that. Okay? So here's a double balloon shape. So this is a P orbital. Okay? Or a representation of the P orbital. All right? That's one of the three P orbitals in the third primary level. I could be drawing it for 2, but I'm drawing it for 3 right now because I'm using just a color coding system here, okay? Now, if you remember, there's the third level. And these P orbitals really aren't inside that third level, so we really need to slice them off right here. Okay? And this part we technically ought to erase. Does that make sense? Now, we don't erase it just because it's kind of hard to mentally imagine that, but you need to know this is actually this top here and this top here make up a P orbital. And there's nothing in between. And electrons can disappear from this node and appear in that node. They disappear out of the universe and suddenly appear in the other one. Okay? Does that make sense? Well, it shouldn't make sense because it seems kind of strange. We don't know of anything that disappears out of the universe and appears somewhere else, but if you're a Star Trek fan, it's kind of the basis behind the whole idea of the so-called transporter in Star Trek. Okay? You can take these subatomic particles and make them disappear from this part of the universe and appear in some other part of the universe. Okay? But if you're not a Star Trek fan, looks like you guys all have empty looks on your faces. You don't have a clue what I'm talking about, which is okay. All right, if you ever watch a Star Trek movie, and there's a new one coming out soon, okay, when they transport people, that you stand in this little thing and you disappear here and suddenly you appear somewhere on a planet somewhere else. This is the idea behind that. Okay, so that's why it's called science fiction. It's actually based on scientific theory. Okay, now we can't do that. All right, we don't have the technology to do that, mind you, but that's the idea. All right? All right, so there's one of our P orbitals. Not all P orbitals, we have 3 of them. So let's find us see if I can find a different color here. I'm kind of running out of colors. Somebody stole some of my colors. So here's another P orbital. And you got to remember, it's really not this bottom part, just the top part. We use 2 balloons because it's easier to visualize, but technically it's just the 2 top parts that's the P orbital itself.